Have you ever really thought about what's happening in that split second when a car lurches forward? Or when you slam on the brakes? I mean, you feel it, right? But how do you actually measure it? Well, today we are diving deep into the physics of acceleration to uncover the secret of capturing those exact, instantaneous changes in speed. Let's get right into it. So, imagine this. A car weaving through city traffic. It's speeding up, it's slowing down, its motion is constantly all over the place. Now, how in the world could you pinpoint its exact acceleration at, say, the 3.2-second mark? It sounds kind of impossible, doesn't it? But trust me, by the end of this, you are going to have the key to solving this exact problem.
All right, so to figure out what's happening at one single instant, we first need to get a handle on the two main ways we talk about acceleration. We're going to start with the big picture and then zoom all the way in.
Okay, first up, we have average acceleration. This is the one you're probably most familiar with, even if you don't realize it. Think about a car's 0 to 60 time. That's a perfect example. You just take the total change in speed and divide it by how long the whole thing took. But, and this is a really important detail, notice the key word here is velocity, not just speed. See, velocity includes direction, so average acceleration gives you a great overall performance number, but it kind of smooths over all the interesting little bumps and changes that happen along the way. But what if you want all those little details? What if you want to know what's happening right now? Well, that's where instantaneous acceleration comes into play. This is what we get when we shrink that time interval down and down and down until it's practically zero. This isn't the acceleration over 5 seconds, this is the acceleration happening this very instant. So here's the bottom line. Average is the whole story, from start to finish. Instantaneous is just one single moment in that story. It's the difference between reading the car's specs in a brochure and actually feeling that G-force push you back in your seat at one specific point in time. Okay, so how do we actually find this instantaneous value? The answer, believe it or not, isn't really in a formula. It's in a picture. We need to look at something called a velocity time graph, because that's where the story of an object's motion really comes to life. This quote right here gives us the absolute key. On this kind of graph, the slope of the line, how steep it is the acceleration. A steeper line means a bigger, faster change in velocity, and that means a higher acceleration. It's literally that direct. Now, when an object is accelerating at a perfectly constant rate, its velocity time graph is just a nice, simple straight line. You can calculate the slope anywhere you want on that line, and guess what? You'll get the same number every single time, because the acceleration just isn't changing. This is our perfect easy mode scenario. But, the real world, it's not always so neat and tidy. That simple, straight line is great for constant acceleration. But what happens when the acceleration itself is changing all the time? How do we handle that? And that brings us right back to our car in city traffic. Because its acceleration is all over the place, its velocity graph isn't a straight line at all. It's a curve. So, how on earth do you find the slope of a curve? A curve doesn't have one slope. Right, look at a curve. Its steepness is different at every single point. And this is the real heart of our problem. If the slope is the acceleration, and the slope is always changing, how do we possibly measure it at just one of those tiny instants? And here it is, the solution. It's a concept that comes from calculus, but the idea itself is incredibly visual and honestly pretty intuitive. It's called the tangent line. Here's how it works. First, you pick the exact moment you care about on your curve. Then you draw a straight line that just barely kisses the curve at that one single point, perfectly matching its steepness in that one little instant. That line you just drew, that's the tangent. And the slope of that simple straight line gives you the instantaneous acceleration. It's this beautiful way of turning a complicated curve into a simple, measurable line, just for a moment. Okay, let's make this crystal clear by looking at a few examples side by side. We're going to see exactly how the shape of a velocity graph directly builds the shape of the acceleration graph. So in our first case, look at the velocity graph on the left. It has a constant positive slope. It's just a straight line heading up. Well, that means the acceleration is constant and positive, which you see as that perfectly flat horizontal line on the acceleration graph on the right. Simple as that. Now let's look at the complete opposite. On the left, you can see the velocity is decreasing steadily, which creates a negative slope. And what does that give us? A constant negative acceleration, which you can see on the right. This is just steady deceleration or slowing down. And what if the velocity graph is totally flat? Well, a flat line has a slope of 0.
So the acceleration must also be 0. This just means the object isn't speeding up or slowing down at all. It's just cruising along at a constant velocity.
This table really sums it all up perfectly. The relationship is so direct and powerful. A zero slope on the velocity graph means zero acceleration. A positive upward slope means positive acceleration, and a negative downward slope means negative acceleration. You see, the two graphs are basically telling the exact same story, just in a slightly different language. So after all that, it really just comes down to this one big, powerful idea. If you want to know the acceleration at any single moment in time, no matter how crazy or complex the motion is, all you have to do is find the slope of the tangent line to the velocity graph at that exact point. That's it. That's the secret.
And I'll leave you with a little brain teaser to chew on. Remember how we said acceleration is a change in velocity? Well, if a car is going around a curve, its speed might be perfectly constant, say 30 miles per hour the whole way around. But is its velocity constant? Something to think about. We'll see you next time.